Chapter 9, Counting and Probability, the Possibility Trees, and the Multiplication Rule. A tree structure is a useful tool for keeping systematic track of all possibilities and situations in which events happen in order. The following example shows how to use such a structure to count the number of different outcomes of a tournament. Now, the tournament consists of teams A and B. They're to play each other repeatedly until one wins 2 games in a row or a total of 3 games. One way in which this tournament can be played out is for A to win the first game, B to win the second, and A to win the third and fourth games. Using that notation there. How many ways can the tournament be played? And assuming that all the ways of playing the tournament are equally likely, what is the probability that 5 games are needed to determine the winner? The possible ways for a tournament to be played are represented by the distinct paths from a root, the start, to a leaf, a terminal point in a tree. Shown sideways this way, down here. The label on each branching indicates the winner of the game. The notation in parentheses indicates the winner of the tournament. The fact that there are 10 paths from the root of the tree to its leaves shows that there are 10 possible ways for the tournament to be played. In 5 cases, A wins, and the other 5, B wins. The least number of games that must be played to determine a winner is 2, and the most that will need to be played is 5. Since all possible ways of playing the tournament are listed in Part A are assumed to be equally likely, the listing shows that 5 games are needed in 4 different cases, and the probability that 5 games are needed is 4 out of 10, or 40%. The multiplication rule. Consider the following example. Suppose the computer installation has 4 input-output units and 3 CPUs. Any input-output unit can be paired with any CPU. How many ways are there to pair an input and output unit with a central processing unit? To answer this question, imagine the pairing of the 2 types of units in a 2-step operation. Choose the I/O unit and then choose the CPU. Possible outcomes can be illustrated in a possibility tree, like so. You got the first 4. The first step would be selecting an input-output unit and then choosing one of the CPUs for each of those options. The topmost path for the root to leaf indicates that input I/O unit A is paired with the CPU X, and so on. Thus, the number of ways to pair the 2 types of units is the same as the number of branches of the tree, which is 4 times 3, or 12. The idea behind this example can be used to prove the following rule. Formal proof uses a mathematical induction and is left to the exercises. If an operation consists of k steps, the first step can be performed in n1 ways. The second step can be performed in n2 ways, regardless of how the first step was performed. And the kth step can be performed in nk ways, regardless of how the preceding steps were learned or performed. Then the entire operation can be performed in n1 times n2 times n3 and so forth to nk different ways. Just multiply the different possibilities out. A certain personal identification number is required to be a sequence of any 4 symbols chosen from the 26 uppercase letters in the Roman alphabet and the 10 digits. How many different pins are possible if repetition of symbols is allowed? How many different pins are possible if repetition of symbols is not allowed? What is the probability that a pin does not have a repeated symbol, assuming that all pins are equally likely? Well, the possible pins, you have 36 choices for slot 1, 36 choices for slot 2, or position 2, 36 for position 3, and 36 for position 4. So it would be 36 times 36 times 36 times 36, which ends up being a little over 1.6 million pins in all, or 36 to the 4th power. The number of possibilities raised to the number of positions being used, power. So, with B making no repetition, choose the first symbol, then choose the second, then choose the fourth again. There are 36 ways to choose the first symbol, 35 ways to choose the second, since the first symbol cannot be used again. 34 ways to choose the third symbol because the first 2 symbols can't be used. And likewise, 33 ways to choose the fourth. So, use the multiplication rule, 36 times 35 times 34 times 33. Thus, with using no repeated symbols, there are a little over 1.4 million different pins with no repeated symbol. C, what is the likelihood of having a pin without a repeating symbol? Take the number of pins with no repeated symbol and divide it by the number of pins possible, and you get about 84% of pins have no repeated symbol. Now the nested loop, a for loop in a program. 1 to 4 for I, J would be 1 to 3. How many times is the inner loop iterated when the algorithm is implemented and run? Now the outer loop is iterated 4 times, and during each iteration of the outer loop, there are 3 iterations of the inner loop. Hence, by the multiplication rule, the total number of iterations of the inner loop is 4 times 3, or 12. Permutations. A permutation is a set of objects. A permutation of a set of objects is an ordering of the objects in a row. For example, the set of elements A, B, and C has 6 permutations. In general, given a set of n objects, how many permutations does the set have? Well, think of it as an n-step operation. First, choose the first element, choose the second element, choose the fourth element, and so on. Any element of the set can be chosen in step 1, so there's n ways to perform that step. Any element except the one chosen in step 1 can be chosen in the second step. So there are n minus 1 ways to perform step 2, and so on. In general, the number of ways to perform each successive step is 1 less than the number of ways to perform the preceding step. At the point where the nth element is chosen, there's only 1 element left, So there's only one way to perform step n. By the multiplication rule, there are n factorial ways to perform the entire operation. There are n factorial permutations of a set of n elements. This reasoning is summarized in the following theorem. For any integer n with n greater than or equal to 1, the number of permutations of a set with n elements is n factorial. How many ways can the letters in the word computer be arranged in a row? How many ways can the letters in the word computer be arranged in if the letters CO must remain next to each other in order as a unit? If the letters of the word computer are randomly arranged in a row, what is the probability that the letters CO remain next to each other as a unit? Well, all 8 letters in the word computer are distinct. So the number of ways in which that you can arrange the letters is equal to the number of permutations of a set of 8 elements, or 8 factorial, or a little over 40,000. If the letter group CO is treated as a unit, then there are effectively only 7 objects that there are to be arranged in a row. Hence, there are 7 factorial permutations, or a little over 5,000 permutations if CO is kept together as a unit. When the letters are arranged randomly in a row, the total number of arrangements is 40,000-ish. And the number of arrangements with CO next to each other in order is, as a unit, is 5,000-ish. Thus, the probability is approximately, it's 12.5% that CO is going to be next to each other. Permutations of selected elements. Well, given the set ABC, there are 6 ways to select 2 letters from the set and write them in order. Each such ordering of 2 elements is called a 2 permutation of A, B, and C, of the set A, B, and C. An R permutation of a set of n elements is an ordered selection of R elements taken from the set of n elements. The number of R permutations of a set of n elements is denoted P of n and R. If n and R are integers, and R is between 1 and n, then the number of R permutations of a set of n elements is given by the formula n times n minus 1 times n minus 2 and so forth to n minus R plus 1. Or equivalently, n factorial over n minus R factorial. So, evaluate P of 2. How many 4 permutations are there a set of 7 objects? How many 5 permutations are there of a set of 5 objects? Well, 5, 2, you would write this way, multiply it out, expand the 5 factorial, cancel out the 3 factorial, and get 20. The number of 4 permutations of a set of 7 objects, again, multiply it out, cancel out the 3 factorial, and end up with 840. Finally, number of 5 permutations of a set of 5 objects, is just going to be 5 factorial, because 5 minus 5 factorial is 1. So it just multiplies out to be 120. So some basic counting there. Now we get into the next section, and we get into counting elements of disjoint sets and the addition rule. Now, disjoint sets are covered in chapter 6, I believe. Basically, a disjoint set is when two sets contain completely different elements. There's no common elements in between them. That's what two just disjoint sets means. Like the set of black cards from a deck of cards and the set of red cards from a deck of cards. They're disjoint sets. There's no commonality between them. So a little bit of terminology there from chapter 6. In this section, we look at counting problems that can be solved by counting the number of elements in the union of two sets, the difference of two sets, or the intersection of two sets. The basic rule underlying the calculation of the number of elements in a union or difference or intersection is the addition rule. This rule states that the number of elements in a union of mutually disjoint finite sets is equal to the sum of the number of elements in each of the component sets. So, say you have a finite set A equals the union of k distinct mutually disjoint subsets, A1, A2, etc. to AK, then the number of elements in A is equal to the number of elements in A1 plus the number of elements in A2, and so on to the number of elements in AK. Pretty much common sense there about the two disjoint sets. If you add them together, you just add the number of elements. Yeah, pretty straightforward. How many three-digit integers are divisible by 5? We looked at that in a previous section. Another way to approach it is this: to use the addition rule. The integers are divisible by 5 are end either in 5 or 0. Thus, the set of all three-digit integers that are divisible by 5 can be split into two mutually disjoint subsets. Three-digit integers that end in 0 and three-digit integers that end in 5. So, how many digits three-digit numbers end in 0? Well, there's 9 choices for the first digit because it can't start with a 0. The second digit has 10 choices. So, because you can have a 0 in the second digit position, therefore, it's 9 times 10, or 90 numbers, three-digit integers that end in the number 0, in the digit 0. Similar reasoning can be used to show that the number of elements that end in 5 are the same. And so the second group also is 90. So by the addition rule, 90 plus 90 is 180, which, if you recall from the previous section that dealt with this problem, was the same answer. So the difference rule. An important consequence of the addition rule is the fact that if the number of elements in set A and the number of elements in a subset B of A are both known, then the number of elements that are in A and not in B can be computed. If A is a finite set and B is a subset of A, then the number of elements in A that are not in B is equal to the number of elements in A minus the number of elements in B. Again, pretty much common sense, but it needs to be said for thoroughness. The difference rule is illustrated in figure 9.3.2. A has n elements, B has k elements, A minus B has n minus k elements. The difference rule holds true for the following reason. If B is a subset of A, then the two sets B and A minus B have no elements in common, and B union with A minus B is equal to A. The U symbol is the symbol that you learn in chapter 6. That means the union of two sets, the joining of two sets. Hence, by the addition rule, n of B plus n of A minus B equals NA. Subtracting for NB from both sides gives the equation n of A minus B equals n of A minus n of B. Consider the personal identification numbers problem again. These are made from exactly 4 symbols, so forth. We went through all that. There are 1.6 million pins with repetition allowed, and 265,000-ish pins with no repeated symbol. How many pins contain at least one repeated symbol? If all pins are equally likely, what is the probability of a randomly chosen pin contains at least one repeated symbol? Well, for A, let S be the set of all pins with repetition allowed, and A be the set of all pins with no repeated symbol. Then S minus A is the set of pins with at least one repeated symbol. And by the difference rule, you get 265,000 pins that contain at least one repeated symbol. Because for 2, there's 2 ways of going about it. Because there are 1.6 million pins in all, and 265,000 of these contain at least one repeated symbol, by the equally likely probability formula from section 1, the probability that a randomly chosen pin contains a repeated symbol is approximately 15.8%. Solution. The other way to approach it is P of A is the probability that the randomly chosen pin has no repeated symbol, so that P of S minus A is the probability that a randomly chosen pin has at least one repeated symbol. Then P of S minus A equals N of S minus A over N of S. By the difference rule, that's N of S minus N of A over N of S, which equals to 1 minus P of A. by the definition of probability and the law of fractions. So 1 minus 8.42 from example 922, you get 0.158 or 15.8% likelihood. Formula for the probability of the complement of an event. If S is a finite sample space and A is an event in S, then the probability of the complement of A is 1 minus the probability of A, where A complement is S minus A. Now, passwords. Certain computer access password consists of 3 through 5 uppercase letters chosen from the 26 letters in the Roman alphabet with repetitions allowed. How many different passwords are there? How many different passwords have no repeated letter? How many different passwords have at least one repeated letter? If all passwords are equally likely, what is the probability that a randomly chosen password has at least one repeated letter? Now, set of all passwords can be partitioned into the subsets consisting of passwords with lengths 3, 4, and 5 because of the addition rule. The total number of password equals to the number with length 3 and the number of length 4 and the number of length 5. Multiplication rule can then be used to compute the number of passwords for each length. Thus, the number of passwords with length 3 is 26 to the third power. Number of passwords with length 4 is 26 to the fourth power. Length 5, 26 to the fifth power. Add that all together, and the number of passwords is a little over 12.25 million passwords. Not very many when you think about it in terms of computers. You'd be able to write a simple program that goes through all 12 million pretty quickly and crack the password, so not too terribly secure here. Constructing a password with length 3 and no repeated letters is a 3-step process with 26 choices for step 1, 25 for 2, and 24 for 3. So there are 26 times 25 times 24 passwords with length 3 with no repeated letter. Similarly, there are 26 times 25 times 24 times 23 passwords with length 4, and similarly with length 5. So the total number of passwords with no repeated letters is those 3 quantities added together, or 8.2 million passwords. Letter C. By part A, the total number of passwords is 12.3 million. By part B, 8.2 million of these passwords do not have a repeated letter. Thus, by the difference rule, the number of passwords with at least one repeating letter is 4 million, a little over 4 million passwords. Given the assumption that all passwords are equally likely, the equally likely probability formula can be used. So the probability that a randomly chosen password has at least one repeated letter is about 4 million divided by 12.3 million, or around 33.1%. The inclusion-exclusion rule. The addition rule says we have how many elements are in a union of sets if the sets are mutually disjoint. Now consider the question of how to determine the number of elements in a union of sets when some of the sets overlap. For simplicity, begin by looking at the union of two sets, A and B, as shown in this figure. The darker shaded area is the union of A and B. The this symbol here is the intersection symbol. It denotes elements that are in both A and B. The union symbol is the combination of both A and B combined together. So go through chapter 6 and you'll learn more about the intersection and that sort of thing. Oh, come on. All right. So, if A and B are any finite sets, then the number of elements in the union of A and B is equal to the number of elements in A plus the number of elements in B minus the number of elements that are in both A and B. The reason being is if you just add the number of elements of A and B together, you'll get the elements that are in both counted twice. So you have to figure out what the elements counted twice are and subtract those from the total. How many integers from 1 through 1,000 are multiples of 3 or multiples of 5? Let's just do that one example. Let A be the set of all integers from 1 to 1,000 that are multiples of 3. Let B be the set of all integers from 1 to 1,000 that are multiples of 5. Then this A union B is the set of all integers from 1 to 1,000 that are multiples of 3 or 5. Let A intersection B equal the set of all integers from 1 to 1,000 that are multiples of both 3 and 5. So, the set of all integers from 1 to 1,000 that are multiples of 5. There should be an NB, I'm not sure what symbol is supposed to be there. Anyway, because every third integer from 3 to 99 is a multiple of 3, each can be represented in the form of 3k for some integer k from 1 through 333. Okay? Hence, there are 333 multiples of 3 from 1 through 1,000. So NA is 333. Similarly, each multiple of 5 from 1 to 1,000 has 5k for some integer k from 1 through 200. Thus, there are 200 multiples of 5 from 1 through 1,000, and if b then equals 200. Finally, each multiple of 15 from 1 to 1,000 has a form of 15k for some integer k from 1 through 66, since 990 equals 66 times 15. Hence, there are 66 multiples of 15 from 1 through 1,000. So the intersection of A and B, the number of elements in that intersection is 66. So it follows by the inclusion-exclusion rule that the union of A and B, the number of elements in the union of A and B, equals the number of elements in A plus the number of elements in B plus the number of, it's supposed to be minus the number of elements in A intersection B, which is equal to 467. So there are 467 integers from 1 through 1,000 that are multiples of 3 or multiples of 5. We skip that one. And anyway, that should be about wrap it up. There's a little bit of a new notation in there for the set theory from set theory in chapter 6. A U union B equals the elements of both A and B. A intersection B equals the elements of A and B. That's the intersection. So the intersection is elements of the set that elements of both A of that are in both A and B, and the union is the elements of from both A and B. Union is easy to remember because the symbol looks like a U, and intersection is just the other symbol. So simple definitions there. You can also look at it this way from the first section, first chapters of the semester. This is similar to the OR symbol that we used in logic at the beginning of the semester. It's a V instead of a U, but it still opens up. That means the elements are either in A or B. So, and this is the elements that are in A and B, kind of like the and symbol from the earlier in the semester. But do the extra credit, chapter 6. It'll give you good explanations of set theory and get you one better on a quiz grade. if you do the homeworks. There's only 4 sections in each section, or in each chapter, so it shouldn't take you too terribly long to go through them. That should just about wrap it up for the day. Have a good day. See you on Tuesday. Enjoy the long weekend.